Welcome everybody to the 8th lecture of the course, where we're going to talk about two main topics. The first one is the transmission matrix, and second one is the signal flow graph. So far we had studied a number of matrices for the microwave network analysis, like Z matrix, Y matrix, and Z matrix, and S matrix, all of those matrices can be defined for arbitrary number of ports. When we come to the applications, they are of course applicable, but there is like a very frequent situation in microwave circuits where we have a number of two-port networks cascaded to one another, and the overall system performance is coming from this cascade of sections. For example, you put an amplifier followed by a filter, followed by another amplifier, so on and so forth. So two-port network cascading is something very frequently encountered in microwave and RF networks. So need for another network analysis tool, another matrix, arose from this fact. So there were a need to a new matrix that is easier to cascade multiple sections. Like, for example, like if this is like a two-port network and we have another two-port network and cascade them, of course, like the system performance is the result of cascading those two parts, or like two two-port networks, and from that need the ABCD matrix were introduced. So what is the ABCD matrix, and why do we need another matrix, and how the ABCD will work is what we're going to discuss here. So the ABCD matrix, or the transmission matrix, is defined as shown here. So it's for only two-port networks. Port 1, we have V1 and I1. I1 is in the direction of input to port 1. V1 is the total voltage at between the terminals of port 1. For port 2, the current I2 is going out of port 2, and the potential V2 is the potential or the voltage between the terminals of port 2. So if we write the ABCD matrix in a matrix format, it would be like this. So we are relating V1, I1 to V2 and I2. So the matrix is ABCD, where V1 equal A, V2 plus B, I2, I1 equal C, V2 plus D, I2. And we need to like pay attention that the current at port 1 is input to the port, at port 2 is out of the port. And that is just to achieve the main feature of the ABCD matrix is the ease of cascading multiple sections. So if we have like two ports, network 1 and another two-port networks 2, that are cascaded to one another, we need to have the overall system performance. So we need to relate V1 I1 to V3 I3. V1 I1 is related to V2 I2 by ABCD matrix 1. So V1 I1 is related to V2 I2. V2 I2 is related to V3 I3. When we cascade them, so we just like replace V2 I2 with this right hand side, we'll have this expression. So the overall system performance after cascading the two networks is the direct multiplication of the transmission matrices. And this is the main advantage or main feature of the ABCD matrix. Of course, the order of multiplication is important because the multiplication process or the multiplication operation is not commutative. So the order must be the same order as the port cascaded. So if you are cascading two-port network 1 to two-port network 2, so we need to multiply matrix 1 to matrix 2. So like the network order must match the matrix order. Also, like, it's good to know that there is another transmission matrix. It's called the T matrix. So it is defined as V plus and V minus on port 1, and it is related. Sometimes some people use it like V2 plus and V2 minus. Some other people use it this way. But here, when we talk about, in our course, when we talk about the transmission matrix, we're going to adopt the definition of the ABCD. I'm just like letting you know there is another matrix that's also called the transmission matrix, and it's used almost the same way for cascading two-port network sections, and it just have a different approach than the ABCD matrix, but our study will be based on the ABCD. And in RF networks and microwave networks, the ABCD is much more familiar, or like much more spread used than the T matrix. So let us do like an exercise on the usage of the ABCD matrix to characterize two-port network. So we have this network here, and we want to find the ABCD matrix for this network. So we go by the definition. The definition of A1 equal V1 over V2 when I2 equals 0. So if we go back here, so A will equal V1 over V2 when I2 equals 0. B will equal V1 over I2 when V2 equals 0. So on and so forth. So we'll just write the definition and evaluate. And when I2 equals 0, what does this mean? It means that port 2 is open circuit. So if port 2 is open circuit and we put V1 here, what is the voltage on this terminal? There is no current, so there is no voltage drop. So V1 will equal V2, so the element A will equal 1. Now for the definition of B will equal V1 over V2, V1 over I2 when V2 equals 0. V2 equals 0 means there is a short circuit here. If we apply the volt V1 here, there will be a current going out of port 2. This current equal V1 divided by Z. So B will equal V1 divided by V1 over Z, which equals Z. Okay, we go for the third element, C. C equal I1 over V2 when I2 equal 0. I2 equals 0. If we put some current here, it will equal I2, so there is no current. If we force I2 to equal 0, we can't put current here, so C will equal 0, because I1 also will equal 0. D equal I1 over I2 when V2 equal 0. So V2 equals 0, short circuit here, current I1 goes in, current I2 goes out, so I1 over I2 equal 1. So the ABCD matrix for this network just have this expression. So it's very common to find in textbooks something like that, the ABCD matrix of like common circuits or like popular circuits, like just a series element, a shunt element, a section of a transmission line, and here we have a transformer, like pi network, T network, so on and so forth. So like those are common sections of microwave and RF circuits, and you would find like sort of a table for the values of ABCD matrix for each of those elements. So that if you have like a multiple like sections cascaded, you can find the overall system by just multiplying the ABCD matrix corresponding to each element of those ones. So as usual, there is a relationship between Z matrix and Y matrix, Z matrix and S matrix, so on and so forth. Also, we can find the relationship between the ABCD matrix and the Z matrix. So we'll take this as an exercise. So we have the ABCD matrix, and so this is the graphical format. And we also, I wrote here the Z matrix. So Z matrix relates V1, V2 on the left side to I1 and I2. But we need to remember here the definition of I2 for Z matrix is going in port 2. The definition of I2 in the ABCD matrix is going out of port 2. So we need to choose which format we're going to adopt. So we're going to adopt the format for ABCD matrix. So I2 of Z matrix must be negative I2, negative this one. So this is the one that we're going to take into consideration. So I2 here would be negative I2 because the direction of the current in ABCD is the opposite of the direction of the current for the Z matrix. Okay, so we need to find the ABCD corresponding to the Z matrix element. So we're writing the equation for V1 and V2 in terms of Z matrix elements, but the current that we are considering is the current definition and direction of the ABCD. So that's why we have the negative sign here. So the A equal V1 over V2 when I2 equals 0. So I2 equals 0. We need to find V1 over V2. So if I2 equals 0, V1 will equal I1 Z11, V2 will equal I1 Z21. So A will equal Z11 divided by Z21. So again, go for the definition of B. B equal V1 divided by I2 when V2 equals 0. V2 equals 0. So we will have I1 Z21 equal, this will equal 0. So those two terms will equal one another. So here V1 over I2. So V1 equal this expression I1 Z11 minus I2 Z12 divided by I2 when V2 equals 0. So this part will give us minus Z12, and the remaining part is Z11 multiplied by I1 over I2. So as we said, when V2 equals 0, I1 over I2 will equal Z22 over Z21. And here is the expression or the value for B. We can write it this way or we can leave it that way. It's the same. Okay, for finding C, so C will equal I1 over V2 when I2 equals 0. So I2 equals 0. I2 equals 0, and we need to find I1. So if I2 equals 0, V2 will equal I1 multiplied by Z21 when I2 equals 0. So we have this relation here, I1 over V2 will equal 1 over Z21. D will equal I1 over I2 when V2 equals 0. V2 equals 0. We just did this before. I1 over I2 will equal Z22 over Z21. So just following the definition of the ABCD matrix, we can relate the ABCD matrix to the Z matrix. The next topic that we're gonna consider in this lecture is signal flow graph. So what is the signal flow graph? It's a useful technique to analyze microwave network in terms of transmission and reflection coefficient. So first we're gonna discuss the feature and construction of signal flow graph. Then we're gonna talk about the techniques for reducing or solving problems. So signal flow graph is composed of just two types of elements, either nodes or branches. So the node is a representation for the input and output power from each board. So each board in the signal flow graph, and here we're talking about electrical board, each board is defined by two nodes. One node, that is, we call it like A, is corresponding to the power going in, or like power or wave entering the board. BI identifies the waves that reflect out of the board. A branch is a path, and it is a directed path, so it's an arrow with direction between two nodes representing the signal flow from one node to the other. So for example, if node 1 is not like we have like some reflection from node 1, so the power that goes in node 1 will be like launched inside A1. The reflection from port 1 will be going out of B1. If there is a transmission from port 1 to port 2, it will go from A1 out of port 2 to B1, sorry, to B2, so on and so forth. And we're going to see this. So for example, here we have, if we have like a two-port networks, of course, signal flow graph can represent any number of nodes for the elements. So here we have two ports. So port 1 will be represented by two nodes, A1 for power in, B1 for power out. Port 2 will be represented also by two nodes, A2 for power in, B2 for power out, and it's very common to draw it this way so that the drawing or the sketch is like clear. We put A1 in front of B2 because there is some transmission signal, and we can put the S parameters for those like two-port network on the signal flow graph. And we can describe things like we can write a story. For example, like a current or a power or wave launched in port 2, part of it will be reflected from port B2, and this amount is S22. One thing related to the branch is directed and it does have a value, so which is the ratio of the signal flow. Part of the signal launched in port 2 will be transmitted to port 1. Transmitted means going out of port 1, so it will go for B1. The value of this amount is S12. And we can tell the story about each branch and each node here in the network the same way. And there is like some special network like termination and source. So for the source, it is implemented this way. So here those points are the same, but we split them to like make it clearer. And here we have like a reflection at the load, gamma L. Here we have a reflection at the source, gamma S. Okay, so this represents a source node, and this represents a termination node. So now we come to the decomposition. So after drawing the signal flow graph, we come to the solution, or we need to reduce the signal flow graph to a simple link like this one. So this is a simple link. For example, here we can say the ratio between V3 over V1, which is the transmission coefficient from port 1 to port 3, equal this quantity. So this is a simple like signal flow graph. So there is a number of rules for simplification or for decomposition of the signal flow graph. Number one is a series rule. When we have two branches in series, we can just combine them, and the value on the branch will equal the multiplication of the values of the cascaded branches. When we have like parallel branches, we can combine them into a single branch where the value on the single branch equals the sum of the two branches. Of course, you can write it mathematically like this, or you can do it graphically like that. Self-loop rule is rule number 3. When we have something like this, again, like it will not make a difference if the arrow is going that way or the arrow is going that way. So there is a loop on V2. So here you can say V2 equal S22 multiplied by V2 plus S21 multiplied by V1. So in order to get rid of this one, we just write the math. We'll write that V2 will equal S21 V1 plus S22 V2. We put the two V2s in the same side. It would be 1 minus S22 multiplied by V2 equal S21 multiplied by V1. So V2 will equal this expression multiplied by V1. So this is called like self-loop rule for decomposition. Splitting rule. So if we have something like that, we can change the place of this node to this point. All what we need to do is to introduce a node here, and the power that goes to this node from V1 will equal S21 going here. So like we can introduce a node to resolve the splitting. Okay, so we can use any kind of combination or sequence of those rules to simplify the signal flow graph, as we're gonna see in the exercise now. Okay, so the example here is requesting to find gamma in and gamma out using signal flow graph of this network. So gamma in is when we have incident here, we'll have a reflection from this port. Gamma out is when we have like a signal here reflected from the load. It will go to the network and part of it will reflect back. So let us first draw the signal flow graph. So here we have, so we know the signal flow graph for this part. We did it before. Here, so the signal flow graph is like this. And now we have like a load to the left, sorry, a source at the left and a load on the right. So we just like connect those two shapes together and we'll have this signal flow graph. So this is the part corresponding to the source. This is the part corresponding to the load. So this is our signal flow graph. We have signal here. The signal goes in, and when we have the signal in, so we have some reflection for the signal that goes out of the network. If there is a mismatch with the source, then we'll have gamma S, and if we have mismatch at the load, we'll have gamma L. We are required to calculate gamma out and calculate gamma in. Okay, so for calculating gamma n, it means that we are looking from here. When the signal goes in, what is the reflected amount that goes out? So the reflected amount, so for gamma n, we're gonna just cut the network at this point. So we are studying this part. Okay, I'm gonna talk about this shortly. So what we are interested in is B1 over A1 under this condition. What is the condition? We have a load here. Okay, so now looking into this part, so we have a loop and we need, for simplification, we can take this part off. How would we take this part off? We just like take this and make it as a separate loop. It doesn't matter if the loop is going this way or it's going that way. So it's a self loop, and we leave gamma L as is. We need to find B1 over A1. So what are the signals that's coming here to B1? There is a direct signal coming from A, and there is a signal coming from here. So this signal that comes to here equal this self loop. So for simplification, we're gonna like simplify those together. It will give us this shape, or like this value. So now the signals that goes to B1 is S11 A1 plus, so now we are using the parallel flow, which we are using parallel rule. So we have S11 plus the other one. The other one, we're going to use the series rule. This value multiplied by this value multiplied by this value. So this is gamma n. For calculating gamma out, so at the source we have gamma s, and what we did is just like we need to take S11 out. So we're going to have this loop placed here. So this loop doesn't matter the direction. So now what is gamma out? Again, gamma out equal A2 divided by going out. So gamma out equal B2 divided by A2. B2 divided by A2, very similar. It's S22 plus the other branch. The other branch is S12 multiplied by gamma S multiplied by this value, which is from the self loop rule. So this way we solved the problem using the signal flow graph. It's simplifying the analysis, but you need to practice so that you can use it correctly. Now just going to talk about a related topic, which is how waveguides are excited. So for transmission line, or for like two conductor waveguide like coaxial cable, exciting them is something that is straightforward. We can apply a potential source, or like a voltage source between the two conductors. So like we can apply a voltage source between the outer conductor and the inner conductor of the coaxial cable, or between the ground and the signal trace for a strip line. So this is how we excite TEM and quasi TEM modes. But for other modes like TE and TM, for single conductor waveguide like rectangular or circular waveguide, how would we excite modes? So in general, we excite modes by either like probe or like loop. Sometimes we are using irises or aperture. So there is a number of ways to do this. We can have like coupling aperture. We can have like a coupling aperture here. There is multiple different ways to excite waveguides. And also we can excite waveguides with loops and probes. I will search for some graphs and put it here in the lecture so that you can have like a feeling how would we excite different modes in waveguides and like single conductor waveguide. And we have homework 4 due in a week, and this is the list of things that we learned today. Thanks everybody for watching the video, and meet you in the discussion session. Goodbye.